All right. Good afternoon, good morning, good evening, class, whatever time it is. This is our day 13 lecture video. So I'm going to share my screen as we go over the schedule here. So for day 13, we're now starting in chapter 5, and this is going to start to wrap up our material for the second test. All right, so for test 2, we're going to be covering chapter 3, so all that intro probability stuff, chapter 4, where we were talked about discrete random variables, and then chapter 5, where we're now going to look at how do we handle probability if the random variable is continuous. Okay. We're doing 5.1 and 5.2 in this video. 5.3 will be covered in the next lecture after this one. And then after that, we will then have our test 2. All right, so that will follow the same way as test 1, online, all that kind of stuff. Of course, if you have questions, by all means, please do reach out, and I'm happy to go over any questions you may have. All right. Let's see. The cat got stuck in here, so let me let her out real quick. All right. She was upset with me for kicking her out, but at least this way she's not going to be messing with stuff in the background. All right, so chapter 5, we're looking at sections 5.1 and 5.2 in this video. So I'm going to go ahead and turn off the screen share as this first example I really kind of want to do on the whiteboard behind me. All right, so section 5.1. And kind of just to back up, kind of give us intuition for why we're doing what we're doing in chapter 5, recall as we keep going back to this coin flipping problem, where if I flip a coin twice, flip a fair coin twice, then we had this probability distribution where I could get two heads, one head, or two heads, or zero heads, one head, or two heads. And we were able to create this probability distribution. All right, so we've seen this before in past lecture videos, where x is the number of heads resulting from the two flips. All right, so this is a random variable. It is a discrete random variable. And for answering probability questions with the discrete random variable, all we're really doing is just adding up these different blocks, right? If I say, well, what is the probability that x could be greater than or equal to 1? Well, there's two different ways x could be greater than or equal to 1. Could be the case that x is 1 or that x is 2. Either way, I would add them together. I would have 1 half plus 1/4 as I add these different columns together to give me this total probability, right? I'm adding these together in order to find my answer, okay? We have a similar notion with continuous random variables where the difference is that I don't have these individual columns or these bars that we can add up, and instead I have a continuous range of possible results. So consider this kind of example, and I'll leave this up for a moment just for reference. Where, all right, well, suppose we have a computer and we ask it to pick a random real number, pick a random real number from 0 to 10. All right. Well, it can pick any possible real number, right? The possible results is now a continuous range, a continuous interval from 0 to 10. It could be any one of these numbers, right? Now, assuming we're not told anything else, assuming it's equally likely to pick any number between 0 and 10, well, then all of these numbers have the same probability, right? So it ends up looking like this flat line for every single possible real number between 0 and 10, and this would be my probability density function, where my probability function is just this constant line. Okay, but what is this height? Well, in the same way as we did before, if I'm thinking of probability as adding up these bars, in other words, it's like I'm trying to find the area under this curve. This entire rectangle here, if I think about the probability of x being between 0 and 10, well, that's 100% of what can happen, right? It can pick any number between 0 and 10. And so if this is my total range of possible numbers for this interval, then this should be 100%, or in other words, the number 1. Well, if the whole area of this rectangle is supposed to be 1, and the area of a rectangle is calculated as length times width, well, the length here along the bottom of the rectangle is 10. That means the height of this rectangle has to be 1/10. All right. So what does this mean? Well, then my probability function is a constant function where for all these x's, I'm getting 1/10 here, right? This constant line. Okay. So for a continuous random variable, as we're trying to add up these bars or add up these different areas, what we're really doing is trying to find the area under the curve. Now, if you've had calculus, Calc 1 or Calc 2, you might already be thinking, well, wait a moment, if all we're trying to do is find the area under the curve, then that's just taking an integral. And you'd be right, that's exactly the strategy we're taking when it comes to continuous random variables. For discrete random variables, I can just add up the individual points. But if I'm looking at, well, when x is 5, for example, if I come back to this picture, well, when x is 5, that's only a single x value, right? That's just a single line. And this line, it doesn't have any width to it. This blue line I just drew, it doesn't have any width. I can't calculate the area of a line because it has no thickness, right? The line doesn't have an area. And so in order to understand probability for a continuous random variable, we're not going to be calculating areas for a single value of x. Instead, I'd look at a range. I would say, well, what's the probability that x is between 0 and 5? Well, that's half of the numbers from 0 to 10. That should be 1/2, right? I mean, after all, if it's equally likely to be any number, for it to be a number from 0 to 5, that's half of the possible numbers. But we can also calculate that as an area question, where the area of this rectangle would be 5 times 1/10, since that's the height. 5 over 10 is 1/2, and so we've calculated its probability. All right. So again, for continuous random variables, calculating its probability and calculating this area under the curve is really kind of the notion we want to get used to with continuous random variables. All right. This example that I just drew, this is actually a type of a continuous random variable called a uniform continuous random variable, or a uniform probability distribution. We'll actually look at these specifically in 5.2 here in a moment. This kind of gives us a nice first example of a continuous random variable, as it can be any possible real number on a continuous interval. All right. So let's come back to the textbook here where we get our definition. So I'll share my screen. And we're given this definition, the probability distribution for a continuous random variable. In other words, this is a function which is determining the probability over a range of different x's. Now in this picture, the purple line represents this probability distribution function, where the height, again, think back to like chapter 2, the height is referencing the frequency. The higher the function is, the higher frequency that x has, and therefore the higher probability. When the function is closer to the x-axis, it gets smaller, closer to 0. It has a lower frequency and therefore a lower probability. But for this picture, if I want to know the probability that my random variable can be between A and B, that means I'm trying to find the area of this region that's shaded in the picture. All right. Since the purple line represents my probability distribution, these are the total kind of relative frequencies for all these different x's for a continuous random variable. And so we find this probability by calculating this area under the curve. All right. So here in the definition, we're told this probability distribution for a continuous random variable represented as a smooth curve, or in other words, some kind of function f of x. It could be a continuous function like we just did, where it's just a flat straight line where it's 1/10 everywhere. It could be something curvy like in this picture. The f function, this probability distribution, can take on a lot of different kind of different looks. It can look very differently. It'll just depend on what kind of application we're trying to model. All right. So this curve is called the density function or the frequency function. And the probability that x falls between some two boundaries, A and B, is the area under that curve between A and B. All right. So this is the working definition we're going to be using. To kind of get practice with this, we want to look at this next example, example 5.1. And I'm going to switch to the whiteboard here as we work through this example. All right. So let me erase what we just did. All right. And we're told that some researchers, this is coming from the textbook, some researchers are looking at the friction that occurs in the paper feeding process for a photocopier. All right. Now, this machine, despite the best efforts of the engineers, the designers who created this machine, there may be some variation, some randomness where it's supposed to produce paper with a certain friction coefficient, but due to some kind of randomness with the machine, it might vary a little bit from what it's supposed to be. Okay? And we're told this friction coefficient is a continuous random variable that measures the degree of friction between two adjacent sheets of paper. All right? This random variable can be modeled using the smooth curve where we have this triangular density function. And we're given this picture. All right? So my x values, they can be any real number between 0.5 up to 1.5, all right? And we have this peak where most of the time the paper is supposed to have this frequency at, or a friction coefficient at 1. That's kind of this peak point that's reached that has this highest frequency, this highest probability. In this case, it's at 0.2. And then it goes down to the right in the same way, and we have this triangle. Okay? Now, with continuous random variables, just like with discrete random variables, the total probability of the entire space has to be 100%. Right? Think back to the discrete random variable properties. All of those probabilities had to add up to 1. It's the same idea here for a continuous random variable, only now that means the total area under the shape or under this curve, or in this case, the triangle, the entire area has to add up to 1, which in this case, it does. I have a base, if you remember some basic geometry, we have a base of 1. We have a height of 0.2. Oh wait, no. I misread that. This was 0. Wow, I really misread this. Yeah, in the textbook you'll see it a little bit better. This was 5, 10, and 15. So the entire base ranges from 5 to 15, all right? So the entire base of this triangle is 10. That makes a little bit more sense. Area of a triangle is base times height divided by 2. And lo and behold, the height, which is 0.2, times 10, the total area here is 1/2 times the base times the height, and we get a total area of 1, just like we're supposed to, okay? So this is a probability distribution as the total area adds up to in this case, the number 1, which is always going to happen for a random variable. Okay? All right, let's look at the question here then. This graph represents our probability density. It's showing us where we have higher frequencies, where we have lower frequencies for different possible friction coefficients, all right, where 10 is the most common guy here, all right? Now, we're asked to find the probability that the friction coefficient is less than 10. All right, so x is my random variable. It is this friction coefficient. Friction coefficient. And it can be any number between 5 and 15, right? It's a continuous range, a continuous interval of possible real numbers for the value of x, right? And we're asked to find the probability that x is less than 10. Well, then, from what we've just seen in 5.1 so far, this means I'm looking for the area under this triangle between 5 and 10. So I'm looking for this shaded region on the graph. Again, we know how to find the area of a triangle. Base times height divided by 2. The base now has a length of 5. The height is still 0.2, and so my answer will be 1/2 times 5 times 0.2, and we'll get an answer here of, that should come out to be 0.5 if you put that into a calculator, right? Let me move my chair out of the way. 0.5. Or in other words, remember this is a percentage, but it's in a decimal format. 0.5 means 50%. Does that make sense? Well, sure. I just shaded half of the triangle, right? Half of the triangle is between 5 to 10. Half of the triangle is from 10 to 15. And so what is probability that x is less than 10? That's half of the possible numbers. We get an answer of 50%, all right? So in general, for continuous random variables, we always have this idea of trying to find the area under the curve. Depending on what kind of probability density function we have, is it something curvy that goes up and down? Is it a straight line? Is it a triangle like this? Depending on what that function looks like, then finding that area under the curve might be easier or harder. If it's something like this, then just basic geometry will work. If it's something weird and curvy, then we might have to use some calculus. Now, of course, this is not a calculus-based class. It's okay if you haven't had calculus. We're actually going to have tables and charts where the integrals have been calculated for us, so we don't have to do the calculus, all right? We'll just have to learn how to read those tables, which have done the calculus for us. But that will be actually at the end of chapter 5. So not in this video, but in the next video, we'll talk about how to handle that. For now, we just want to get used to this idea of how to handle continuous random variables. Okay? So this is actually 5.1 is a very small section, and this is the one and only example that the textbook gives. So next, we would like to look at section 5.2. And so I'll go ahead and share my screen here actually, because we already did an example like this a moment ago. Where here we're talking about the uniform distribution. Uniform distributions, just like this picture in the textbook, always look like these kinds of rectangles. We call it uniform because continuous random variables that appear to have equally likely, right here in the text, oh, here we go, equally likely outcomes over their range of possible values. So it's equally likely to be any possible x, so then the frequency is just as high for every possible x, and it gives a line, which is a straight flat line, as our probability function, our probability distribution density function. And so when this happens, this is like the example we started with in this video, where we have a computer randomly picking a real number between 0 and 10, it's equally likely to be any number between 0 and 10, and so it creates this kind of rectangle picture. All right. Just as we said earlier, the total area of this rectangle has to equal 1. Why? It's a probability space. And for every probability space, if you look at the entire space of what can happen, if you look at all of the possible outcomes, that should total 100%. And 100% as a decimal is the number 1. All right? So the area of this rectangle is always 1, in which case, depending on what your base is, how long your base is, that's going to change the height. All right. So I'm going to do this on the board here, so I think that'll be easier than just reading this off to us from the textbook. So what we end up with here, and let's see, the textbook is using D and C as the boundaries, so I'll use D and C as well. So suppose we have X can be any real number between C and D, whatever they are, right? So on the real number line, assuming that C is less than D, that means C is to the left, D is to the right because D is bigger. And so then the random variable can be any number between C and D, right? Now, assume that each possible result of the random variable, each possible outcome is equally likely. All right. In which case, its frequency, well, how common are each of these possible answers, has to be a straight line. If they're equally likely to happen, they all have the same frequency, the same relative frequency. And so we end up with this rectangle. Now, the area of the entire rectangle, area of entire rectangle, has to equal 1, right? So if I have this length, which in total is D minus C, right? If D is bigger than C, then D minus C will tell me how long this portion is. That's some length, just like we did earlier when we had 30 minus 10, right? Or 0 and 10. I forget what number I came up with earlier. At any rate, this is some length. But the entire area of this rectangle has to equal 1, length times width. And so the height of this rectangle has to be 1 divided by D minus C. All right? This way, as I multiply the height times the width of this rectangle, the total area will always equal 1. And once we have that, well, now I can find the probability for any range I like. So what is the probability that X can be between A and B? Well, that depends on what A and B are. Now, presumably A and B, because X can only be between C and D, then just like we did earlier with the computer example, this A and B, this is some region in between C and D. So A and B, whatever this is. In which case, to find this area, I'm looking for the area of this shaded region. What's its probability? Well, it should be length times width times length, right? Or in other words, the height times the width. Well, the total width here is B minus A, assuming that B is the bigger guy. That's B minus A times, well, whatever my height is, 1 divided by D minus C. And so for every single uniform probability distribution, this is always going to be kind of the approach with what happens here. Depending on how far apart your range of possible values are for your random variable, that gives you a length, a total length, which then tells us what the height has to be in order for the total area to be 1. Once you know that height, then the probability of some smaller region is the length of that smaller region times the height we found. Again, just basic geometry, length times width is giving me the area of this rectangle. And so for any uniform random, or for any uniform probability distribution, this is always the idea. We call it uniform because it's equally likely to be any x value, hence the probabilities are uniform. All right. So we'll come back to the textbook here for a moment as I share my screen again. And so they give us this breakdown, the same thing we just talked about. It's probability density function. It's this fixed constant number. We saw earlier with the computer example, I think it was between 0 and 10. But its height was 1/10, right? And so its probability density function was equal to a constant number of 1/10 to have that constant height, right? Now, the average, because it's uniform, it's always just the dead middle. What's your maximum number plus your minimum number and finding what's the middle between them? Well, that's taking an average, right? Add two numbers together, divide them by 2. That will find the exact middle. And so, like the example where it could pick a random number between 0 and 10, the average number there would be 5 because it's the exact middle between 0 and 10. Now, they also give here for uniform random variables, the standard deviation, we have this formula, the maximum minus the minimum divided by the square root of 12. The reason the standard deviation is doing that is actually getting into some weird calculus kind of stuff, which we're not going to be doing in this class. So don't worry about that too much. It's not super important you remember that. You might see it pop up on a homework question, but that's not something I'm going to test you on. That's not something that will pop up on a test. All right. But being able to find the average, that's something we can do fairly easily without calculus, where we're just looking for the middle between the maximum and minimum values here, between D and C. We also see the probability of the region then, well, it's a rectangle. Find the length of, or the base of this rectangle, that's B minus A, times the height, which is 1 over D minus C. Well, that's a fraction. When you multiply B minus A times that fraction, D minus A is just in the numerator of this fraction. And so this gives us the same calculation that we had here on the board. All right. And so we can find the probability for any uniform continuous random variable using this kind of thought process. All right. Which leads us to this example we want to look at from the textbook, where we're asked about this car dealer, where he's selling these cars that he knows they're going to have a major breakdown in the next 6 months. They're just not in good shape mechanically, and he just wants to get rid of them before they break down. But in order to try to, make customers feel better about buying his cars, he tells them, yeah, I'm going to give you a warranty for 45 days so you can return it to me, no problem. Um, but beyond that, then the warranty expires. Is this a good deal? Why is he making this promise? Well, think of this as a uniform random variable. And so let's go to the whiteboard here behind me. All right. This is example 5.2 from the textbook. All right. Where here, now assuming it's equally likely to break down, let's let X be how many months pass before the car breaks down, right? So X is the number of months before the car breaks down. All right. Well, the salesman, he knows it's going to break down the next 6 months, or somehow he knows this, or he expects it's going to break the next 6 months, right? But it could be any time between now and 6 months later, right? So X could be any number between 0 and 6 months. 0 months and 6 months. All right. We're also assuming here that it is equally likely to be any moment between 0 and 6 months. All right, so we're dealing with a continuous random variable. It can be any possible real number between 0 and 6. And we're also assuming this is uniform. It's equally likely to be any moment. Okay? So what does this mean? We can draw a picture. It could be any time between 0 and 6 months, and it's equally likely. All right? So then what is its height? Well, the total base of this rectangle is 6. The entire area has to add up to 1. It has to have an area of 1. And so length times width, then the height of this rectangle has to be 1 over 6. Okay, so not too surprising. And now he gives a warranty of 45 days. Now in months' time, that means it's a warranty of 1.5 months. Okay. Is that actually a good deal? Well, think about the average here. On average, when would these cars be breaking down? Well, the average, again using the Greek letter mu here, is supposed to be the dead middle between 0 and 6. Well, 6 plus 0 divided by 2 is 3. So on average, these cars are going to break down around 3 months, which is exactly why the salesman doesn't care about this warranty. He can tell customers, oh yeah, I'll give you a 45-day warranty, no problem. But he knows that on average, they're not going to break down yet. It may take 3 months before they break down. If it's equally likely to be anything between 0 and 6, the odds are that he's going to be okay. It's going to break down after the warranty, and then he gets to walk away with the money. All right. So his warranty makes sense in terms of his business, but that warranty should not be comforting as far as a potential customer. All right. So we can calculate the average here based on this continuous uniform random variable. All right. This also leads us into today's participation question. This is for participation day 13, where we're dealing with the same car salesman. And now the question asks, calculate the probability that the car will break down while it's under warranty. In other words, find the probability that X is less than or equal to 1.5, right? If X is the number of months before the car breaks down. Well, then I'm looking for this region between 0 and 1.5, and I want to calculate its area. Again, length times width. The total length of this rectangle is 1.5 times a height of 1 over 6. We then go to a calculator, and we find 1.5 divided by 6 gives us 0.25, or in other words, 25%. So, I mean, yeah, for this salesman, there is a 25% chance that the car could break down while it's under warranty, and then the salesman would have to give the money back, right? But most of the time, the other 75% of the time, the car is going to break down after the warranty, and the salesman gets to keep the money. So, sure, sometimes he's going to have to pay out, but most of the time, he's keeping the money for himself, and then the customer is the one who's out a car that's no longer working. All right. So this is a kind of model that the salesman would like, but again, would not be beneficial to the customer. Okay. That gives us our answer for today's participation question. And then returning to the textbook, that's also our last example in 5.2. So both 5.1 and 5.2 are much smaller textbook sections. So this video may be a little bit short, but that's okay. Take the time, work on homework, or go back and catch up with other lecture videos. Make sure you understand what's happening. 5.3, as we wrap up chapter 5 in the next lecture video, is much larger and a much bigger deal for what we're going to be doing in the future as we continue into chapter 6. All right. So we'll be talking about that in the day 14 lecture. Of course, if you have any questions regarding the homework or tests or anything with the class, please feel free to message me, email me, come by office hours, let me know what's going on, and I'm happy to help. But otherwise, that's going to be it for this video. Um, I wish you the best of luck, and I will see you in the next video. All right. Have a good day.